This is chapter 13F on real life graphs. In this chapter, you'll learn how to interpret graphs for information, but also how to make graphs for applied situations. So first, let's look at an example of problem. Janina goes to the shop for her mother, and this graph describes her journey. So if we look at this graph, on the x-axis, we notice it's about time in minutes. If we look at the y-axis, we notice it's talking about distance in meters and the distance from home that she travels. Then we see the line, and it goes up, across, and then down. How far away is the shop? How long did it take Janina to get there? How long did she spend at the shop, and was she going faster going or coming back? Now, as we look at this graph, as the numbers zero is basically indicating where she starts. This is home. And as she travels further away, distance increases. So we'll notice that as she walks for 5 minutes, that it seems like her distance moves farther away. Here we notice for about 10 minutes that her distance stays the same. It stays at 800 exactly. And then we notice that in the next 10 minutes passing, that her distance seems to go from 800 back down to 0, which indicates something else. So given those little bits of information, can you answer the following questions? Pause. So let's take a look. How far away is the shop? So since she goes from home and she travels all the way to 800, all of a sudden she stops moving any extra distance. This indicates that at this point, this is the shop. Apparently the shop is 800 meters away. How long did it take Janina to get there? So to get from 0 to 800, it took her 5 minutes. How long did she spend at the shop? Now, we can tell that she spent 10 minutes at the shop, 5 to 15, because the line is straight. This indicates that there is no change in her distance, that she stayed at the shop for that long. So she stayed there for 10 minutes. And then, was she faster going or coming back? So the steeper the line, the faster it is. So if we were to compare a line like this versus a line that was a little flatter, we would say that this is faster because it rises faster, whereas this one rises slower. Going downwards, it's the same idea. If we're going this way versus that way, if you imagine a slide, this one you can imagine is faster, and you can imagine that this one is a slower. So was she faster going or coming back? Well, given that this line seems steeper than this line, she was faster going to the shop. Now, making a graph in application. In a science lesson, the length, L centimeters, of a spring is increased by adding masses of m kilograms to one end, so that this equation, L equals 20 plus 1/4 m. So basically, we're given an equation to describe the situation. Now, step A, draw a graph of L against M. What mass is needed for the length to be 23 centimeters, and what is the unstretched length of the spring? So to give you a hint on how to start drawing a graph for this equation, you have to remember to make a table of values. And in this case, L, being it by itself, is our answer. It's kind of like Y. And M, being that it's in the equation, is our X. So L is really dependent on whatever M is. The answer for L will be given once we figure out what M is. And you're like thinking, well, how do I know what to give M for values? You're the one who controls M. And so since you control M, you can really give it any values to make this work. So for me, I always like to use at least a 0 to start. And then from there, I might use, since we're working with a fraction here, 1/4, I'm going to use numbers I can divide by 4. So I'm going to use 4, 8, and 12. If you use numbers like 2, 3, 5, you can do that. It's just, it will be a little more challenging given that we have to multiply by a fraction of 1/4, which also means timesing by 1/4, which also means to divide by 4. So at this time, pause and complete this table before you draw your graph. Okay, so here we go. If my equation is this, then I'm going to go ahead and substitute the values of m into this expression to get my answers for L. So 20 plus 1/4 times 0, well, that's going to give me 20 because anything times 0 is just plain 0. Then I'll do it again. 20 plus 1/4 times 4. Well, 4 divided by 4 is 1 plus 20 is 21. Then I do the same thing with 8. 20 plus 1/4 times 8. Well, 8 divided by 4 is 2 plus 20 is 22. And you can start to see a pattern here since I counted by 4, so the next one will be 23. Okay, so now you have your table of values. You can use this to draw your graph. So looking at your graph, look at this. Your x values must start at 0 and they must at least go to 12. And your y values for your L must go at least to the number 23. So when you draw your axes, of course you would draw it much straighter than me. Allow yourself, and given whatever space you have, make it work. So I will go ahead and since I used up to 12, I'll make each one equal to 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I need up to 23 at least. And I don't think this piece of graph will go to 23. So I'm going to go ahead and count by 2's. So this is my 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. This is a little tricky to write on here. 22, 24, and 26. Make sure you label which each side represents. M to represent kilograms, and L to represent centimeters, length. Recall from the table, at 0 it was 20. At 4 it was 21. So it's right in the middle. At 8 it was 23 or 22. At 12, it was 23. 20, 21, 22, 23, yes. Then from there, take your ruler and draw a straight line through. So that is how you draw a graph for A. Now the question is, B, what mass is needed for the length to be 23 centimeters? Well, coincidentally, we actually did solve that. We know that in order for the length to be at 23 centimeters, we actually had to have a mass of 12. Another way you can do it is you look directly at your graph, and your graph is probably more clear than mine, and go straight across to where it says, to where it is 23. So in my case, mine is not perfect. And you go straight down, and that'll tell you your mass. So in this case, the mass should be 12 kilograms. And when they're asking for the unstretched length of the spring, they're asking you for what is the length when the mass is 0. Because when you have no mass, it doesn't stretch. So what is the mass when it's 0? Or what is the length when the mass is 0? In that case, it's 20 centimeters. So when it comes to these word problems, it comes into your ability to interpret the information and read very carefully. It's everything we've done before in previous chapters, but now it's just applied and just takes a little bit of time to read and understand what it's saying. that's it.